All right, so I wanted to put this video together to let you know a little bit more about states of matter and types of materials and how particles are organized in these materials. It's really important to have a very good mental model of how different substances states are organized at a molecular or atomic level, because at its fundamental, if you think about chemistry, we're really going to be learning about these atoms and molecules, their reactivity, how they interact with other things, how they behave, but it always comes back to individual particles, whether those be atoms or molecules. So having a good mental picture of how these are organized is very, very useful. All right, so whether we're talking about atoms or molecules, all material really exists in three common states of matter. All right, we've got the gases, the liquids, and the solids. And these are essentially phases or forms that matter exists within. It turns out that any particular substance can exist in all three, typically. But under normal circumstances that we interact with that material in our everyday lives, it usually takes a characteristic phase. Now let's spend a few more minutes talking about each phase and understanding the major characteristics of each. We're going to start with gases. Gases will have a varying shape. Gases will always diffuse to fill the shape of a container in which they're placed. Gases do not have surfaces, and gases will always freely mix with one another. They'll mix well due to diffusion. The reason why this is because that particles of gases are always in random straight line motion until they collide with something else. This could be another gas particle, same composition or different, or perhaps they collide with the wall of the container. This is how gases exert pressure, and one of the typical things of gas behavior. Now, particles which are in the gas, this can again be atoms or molecules, will have a little bit larger distance between them compared to the condensed phases, that is, liquids and solids. So in gases, the particles are a little bit further apart, and consequently, the particles do not interact with one another as much in these condensed phases. Now, when I say interact, what I mean by that is molecule A and molecule B exerting a force on one another. These are called intermolecular forces. We'll learn more about these later. They're actually very, very important for the way materials exist in our world. Gases have very weak intermolecular forces. Now, that's not to say that different gases can't react, because they do react in many cases, and we'll see examples of that throughout the class. But what's important to understand is that the distance, the average distance, between molecules or atoms in the gas phase is usually much greater than in liquids and solids. Now, if I was to actually break out a ruler and measure how far apart the gas molecules were, it would actually be a pretty short distance, maybe on the order of micrometers, okay? That sounds very small, but it's actually thousands of times greater than the distances between molecules in liquids and solids. So gases are mostly empty spaced, and as a result, they can be compressed. To explain a little bit more about gas behavior, I'd like you to view this video right now, which shows how particles of gases move.
Velocity as a result of collisions with other particles and with the walls of the container.
Liquids are relatively incompressible because the particles which make up liquids are close together, though not as close together as the particles in a solid. Liquids conform to the shapes but not the volumes of their containers because their particles can and do slide randomly past one another.
As you can see in the animation, the liquid particles shown in blue are also in continuous motion, but because they're so close to their nearest neighbor, they'll likely collide with a neighbor very quickly as compared to a gas, which will have much larger mean free path before collision.
Ice is held together as a solid by hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
Solids are virtually incompressible because the particles, which make up solids, are close together. Solids do not conform to the shapes or the volumes of their containers, because their particles have relatively fixed positions in a regular three-dimensional array. The particles cannot slide past one another.
It is important to realize that the particles in solids are in small vibrational motion if the temperature is above absolute zero. However, the ability for the particles, the atoms or molecules, to undergo translational motion, that's the motion left and right, front and back, up and down, in solids, that translation is far more restricted than it is in liquids, and a lot more restricted than it is in gases. Now, when speaking of solids, there are really two different fundamental classes or types of solids. We have crystalline solids and amorphous solids. And while both of these are solids, there's a freedom of movement of the fundamental particles. If we were to actually look at these two different types or categories of solids on a molecular or particulate level, we'd see very, very different things. For instance, for amorphous solids, they really lack a definite organization. If we were to look at the particles in an amorphous solid on a molecular level, it would look like this figure on the right with the blue and the green dots. These are representative of the fundamental particles or molecules that make up this particular amorphous solid. It's just an imaginary substance. However, you can see there's no long-range order or organization with how this solid's put together. All these particles are just sort of clumped together in random arrangements. Many solids, however, are amorphous, like glass, for instance, or rubber. Now, on the other hand, the crystalline solids, which are shown on the left, are very different, because if I was to look at a crystalline solid to see the actual arrangement of the particles, what I would see is that the particles are arranged into very specific and precise repeating units. Many ionic compounds are crystalline solids. One common example of this is table salt, sodium chloride. It's made up of sodium ions, which are cations, they're positively charged, and chloride anions. Anions are always negatively charged. In this picture, we see an example of how sodium chloride or table salt might arrange itself. And you can see that it arranges itself into a three-dimensional lattice of repeating ions, such that they sort of offset one another. The positives and negatives offset one another. It's a very specific long-range order, and this is what's characteristic of crystalline solids. Crystalline solids need not be ionic. They can also be molecular in nature. For instance, ice is a good example of a crystalline solid. Here we can see pictures of water molecules, H2O, and the figure with the dark black background, the red is the oxygen and the white spheres are representative of the hydrogen, hence H2O. And you can see many water molecules coming together to form a complex three-dimensional structure that's characteristic of ice. So ice is an example of a crystalline solid as well. So while we're on this subject of organization of matter, I wanted to consider briefly another topic near and dear to my heart so that we can all say that we understand this here at the onset of class. Think about life experience. When you go into your kitchen and maybe get a glass of water or dissolve some salt or sugar in that water, what happens? Well, clearly the salt and sugar dissolves. I think everybody's familiar with such an experiment. But what really goes on a molecular level? That's what we want to concentrate on and learn some terminology here for the next couple seconds. Well, when we take our salt and our sugar and we dissolve it in water, clearly the material that we dissolve doesn't just disappear or vanish. Something else must happen. And in fact, a very interesting thing does occur. Those solids will dissolve in the water to form a solution. A mixture is called a solution in this case, okay? Now the solute is the solid that we dissolve in the water, and the water itself is called the solvent. Just some terminology for you. Now a very interesting thing occurs when the solid dissolves in the water. The solute molecules, or ions, that is the salt or the sugar, will become surrounded by water molecules. Water is a polar molecule. It has a positive and a negative end. So it can actually form energetically favorable interactions with the ions when water molecules surround the ions. This stabilizes the dissolution process. The ions, or solutes, are said to become hydrated as a result, which basically just means they're surrounded by many water molecules. This forms what's known as aqueous solutions. You'll see that a lot in this class, aqueous solutions. Usually you'll see an ion in a chemical reaction that's followed by the letters AQ in a parentheses. And that's what we're talking about. So that's all we need here, basically a solution, a water-based solution of a material dissolved up in water. That's what the definition of aqueous is. And the ions, again, are said to be hydrated. So we know that any substance, whether it's a molecular substance or an element that exists as atoms, can undergo changes in states of matter. It can move between a gas, a liquid, and a solid. And a phase change like this is an example of what's known as a physical change. A physical change is a change that alters a substance's physical properties, but not its chemical composition. This is important. The physical change only alters the physical properties of the material, not the composition. If the composition changes, that is an example of a chemical change. More on that in a second. But what are some examples of physical changes and some associated vocabulary that's associated with these physical changes? Listed on this slide. One physical change is evaporation. I think everyone's familiar with this. If you leave a glass of water out, it'll evaporate. This is when a liquid gets transformed into a gas without any chemical change. Now, condensation is when a gas turns into a liquid. This might be a little bit less familiar to us. However, on a humid morning, if you go out to your car and you see a lot of water condensed on the windshield, that's an example of condensation. If it didn't rain, that got there just because of condensation, this conversion from the gas phase to a liquid. And there's also sublimation. Sublimation is when we go from a solid directly to a gas. This is even less familiar to us. However, there is a common example. Think about dry ice. Dry ice is not water, it's carbon dioxide. Actually sublimes directly from a solid into a gas. Never goes through the liquid state. And this is what's characteristic of sublimation. Direct from the solid to a gas. Now, deposition is the opposite. This is where we go from a gas to a solid. Deposition, we don't necessarily encounter that much in our daily life. However, it's a really important industrial process to make coatings and things of the sort. Now there's melting. Everyone's familiar with melting. This is where we go from a solid to a liquid. Think about an ice cube that you allow to melt in a glass on a hot summer day. That's melting. And lastly, there's freezing. You know, in the winter, liquid water can freeze into solid ice. This is an example of freezing, where we go from a liquid to a solid. So be familiar with this vocabulary and be able to identify different phase changes. You'll be able to want to define these terms. That could be important for exams. Now, in contrast to physical properties, chemical properties are innate characteristics that a substance exhibits when it interacts with other material or other matter. For instance, we all know that gasoline is flammable. This is because it reacts with oxygen to carry out a chemical reaction. This is a chemical property of gasoline. Iron rusts. If you leave it out, it's also a reaction with oxygen, oftentimes mediated by water, but it's an example of a chemical property of iron. Hydrochloric acid's corrosive, another chemical property. And that leads us to chemical change, or chemical reactions. How would we define a chemical reaction? Well, it could be described as being an event in which one or more substances is converted into one or more different substances with different composition and different properties from the original. In a chemical reaction, we take certain molecules and we make them into new molecules. Maybe they decompose into simpler substances. Maybe we make them more complicated substances. But there's always a change in their molecular composition. And as a result, the products of the reaction will have different properties than what we started with. Oftentimes, you can get hints that chemical reactions have occurred by changes in color, changes in temperature of the sample as heat is either evolved or captured from the surroundings, generation of a gas, maybe you see an odor change, or formation of a solid precipitate. All these are hints that a chemical reaction has taken place. So in a nutshell, new substances will always form in chemical reactions. Chemical bonds are broken, formed, or rearranged. Alright, now that we know about chemical and physical changes and what they involve, let's try some sample problems. I got this actually just directly out of your textbook. It's become pretty popular to show this kind of thing as a question in textbooks, to show that you're really thinking about and understanding what's going on. And what you're faced with in this problem here, 1.1a at the top, is the following change, chemical or physical. And what they show you is an artist's rendering of some sort of change, okay? We got to figure out, is it chemical change or physical change? To do that, we got to consider the circular volume on the left as it compares to the circular volume on the right of the arrow. Now over on the left, if we look at very carefully what's inside that circular volume, which is representative of our sample of matter, we see that we've got some molecules, which are red spheres, apparently bonded to these blue spheres. Now we don't know what element they are, what molecule it is. This is just a cartoon picture, right? But the red and the blue appear to be paired up. In addition to that, it looks like we've got 3 individual red spheres on that left-hand side. Now, we have our arrow. The arrows always denote change, whether that's chemical or physical. We'll decide that in a second, but some kind of change that's occurred. And then on the right, what do we've got? Well, we've got our same volume. Now we've got blue spheres by themselves, and the red spheres are all paired up. See that? So carefully pay attention to what's changing as a result of the process that's under study. Now, generally speaking, when you're considering these cartoonish pictures that show spheres, red spheres, blue spheres, white spheres, whatever colors, each of those spheres are representative of a particular atom or element from the periodic table. So in this case, the fact that the colors of the spheres in terms of which ones are paired up are changing. On the left, we've got the red and the blue, and then on the right, we've got the red and the red. To me, that's indicative of chemical change, because it looks like bonds are breaking, new bonds are forming. This is consistent with a chemical reaction, a chemical change, all right? Now, in 1.1b on the bottom, we have a little different situation, because here we've got our volume, and in that volume on the left-hand side of the arrow, it's just 8 red spheres down at the bottom. Now, the change that occurs suggests that those 8 red spheres are now basically dispersed throughout the volume. Okay, they've even got these little, I don't know what to call them, tails behind the spheres that indicate that these spheres might now be in more rapid motion, linear and straight line motion, than they were originally. Where originally on the left, it looks like they're pretty static down there at the bottom. So thinking about what happens here, it looks like we've taken a bunch of red spheres and just dispersed them throughout the volume. There's not really been any bonds broken or new bonds formed. It's just more dispersed. The material is more dispersed. So when I look at this cartoon picture, I think that it's more reminiscent of, say, evaporation or maybe sublimation, where a liquid or a solid gets converted into a gas. Okay, so this latter process in 1.1b, to me, represents a physical change.